Hi everyone, I'm Irene Uriarte,
And I'm Francisco Aponte.
and today we're excited to share our final project, an analysis of global shipping patterns and how data can help us understand the backbone of world trade. Shipping affects everything from grocery prices to delivery delays, and we wanted to break down what's actually happening behind the scenes. So let's dive in.
Our project focused on four big ideas. First, understanding how global seaborne trade is distributed across countries. Second, how efficiently ports operate, especially through metrics like dwell time. Third, how COVID disrupted shipping volumes around the world. And finally, why a handful of countries consistently dominate global maritime trade. By exploring these questions, we wanted to connect big picture trends and with real-world consequences.
We chose this topic because global trade isn't abstract. It impacts our daily lives in ways we don't usually think about. Whether it's the price of food, the time it takes packages to arrive, or shortages during crises, shipping is at the center of it. We also both have personal interest in logistics, operations, and international trade. And honestly, another big factor was data availability. Shipping has tons of open data sets, which made this an ideal real-world topic to analyze using Python.
Before writing any code, we had a few expectations. We expected only a handful of countries, mainly China, the US, and a few others, to dominate global shipping. We also assumed Asian ports would be more stable and efficient than US ports. And of course, we expected COVID to have caused major disruptions, followed by an uneven recovery across countries. The rest of this presentation walks through how our data either confirmed or challenged these assumptions.
To answer our questions, we combined four key data sets that each provided a different view of global shipping. We used UNCTAD's seaborne trade data, the US BTS API for port dwell times, a scrape table of the world's busiest ports for TEU volumes, and the World Bank API for standardized TEU traffic. Together, these sources gave us global trade trends, port efficiency metrics, and container volumes comparisons across countries. A TEU is a 20-foot equivalent unit, the standard measure of container capacity, and a 20-foot container equals 1 TEU, and a 40-foot container equals 2 TEUs.
Our cleaning process was one of the most critical steps. We removed regional labels like Asia or developing economies to avoid double counting and filtered everything to 2013 and 2023 for a consistent 10-year window. We used PD.numeric to numeric to fix messy values and then grouped by country and year to create meaningful averages and totals. For our regression in Insight 4, we built a numerical time index so the model could capture dwell time trends. Cleaning wasn't flashy, but without it, none of our insights would have been reliable.
Here we are cleaning the main UNCTAD seaborne trade dataset. We start by reading the CSV and keeping only the columns we actually need, so the year, country label, cargo type, and total metric tons. The original file reports metric tons in thousands, so in this function we convert those values into actual tons by multiplying by 1,000 and turning the column into numeric data.
This function cleans the US dwell time data from the BTS API. The API returns a JSON, so we first convert it to a data frame and keep the year, month, and hours. Then we convert everything to numeric and transform hours into days of dwell time, which is easier to interpret. After sorting by time, we group by year to compute the average dwell time days per year, which is what we later use in our regression insight. We also add a couple of extra columns, a month-to-month change in dwell time, and a delay flag that marks values that are more than 2 standard deviations above the mean. That gives us a quick way to spot unusually congested months.
This function handles our web scraping. We pull the Wikipedia page for the world's busiest container ports, use Beautiful Soup to extract the main table, and convert it into a data frame with read HTML. We keep only the port, country, and TEU columns, clean the strings so TEUs become numeric, drop invalid rows, and sort by TEU volume. We then assign global ranks, compute each port's share of total TEUs, and aggregate TEUs by country. This clean TEU dataset is what we later use to compare countries like China, the US, and Singapore.
This function pulls TEU data for the US, China, and Singapore from the World Bank API. We flatten the nested JSON with JSON_normalize, clean and convert the year and TEU values to numeric, and filter 2020-2023 to match our other datasets. Then we grouped by country to compute average TEUs, calculate year to year and percent changes, and add flag for incentive above 10%. This gives us both the long run averages and the short term volatility needed for our analysis.
This slide shows the code behind Insight 1, where we measure how concentrated global seaborne trade is. We load the clean dataset, remove regional labels so only real countries remain, and group by country and year to get total metric tons per year. Then we average each country's totals across 2013 to 2023 and compute their percentage of the global sum. Finally, we sort and keep the top 10. This is what drives the donut chart, showing how a small set of countries, especially China, dominate global maritime trade. With that code, our first insight becomes clear. Global seaborne trade is highly concentrated. China alone handles about 13% of all cargo, and the top 10 countries together manage over half of the global volume. This level of concentration matters because disruptions in any of these major players can quickly affect the entire global economy. It sets the tone for the rest of our project by showing how uneven and vulnerable the world's shipping network really is. For our second insight, trade volume stability, the coefficient of variance analysis, we loaded the Clean World Bank TU CSV, then filtered TU data from 2010 to 2021. We grouped by name to compute the average TUs and standard deviation, and we created the coefficient of variance, which was calculated by dividing the standard TU by the average TU for each country, and then we sorted countries by coefficient of variance from most to least volatile.
Using average TEUs, standard deviation, and the coefficient of variation, we found that China is the most volatile, the US shows moderate swings, and Singapore is the most stable of all. This matters because higher volatility creates more pressure on port capacity, while stable flow make planning and operations much easier.
This code powers Insight 3, where we compare pre-COVID and post-COVID trade volumes. We load the clean seaborne trade data, remove regional labels, keep the data from 2013 to 2023, and group by country and year. Then we focus on the major post-COVID movers by filtering to countries with the highest 2022 to 2023 volumes. We compute each country's pre-COVID and post-COVID average, calculate the recovery percentage, and sort the results to find the top 10. We created this visualization for our Insight 3, and here we can see that countries like Malaysia and Turkey had the strongest rebounds, and surprisingly, China and the US had moderate recovery percentages due to higher pre-COVID baselines, and this reflects their stability to withstand COVID disruptions better than smaller economies.
For our Insight 4, we called the web parser 1 to pull the clean BTS dwell time data. We created a month index column as a numeric time axis, so it goes from 1 to 53 for 3 years. We defined features X equals month index and target Y equals days. And then we trained the linear regression model on this historical data. And using that same historical data, we predicted the next month's forecast using the linear regression model. For Insight, the trend line slopes slightly upward post-COVID, which means that there hasn't really been a full recovery. And the model predicts that 1.39 days of dwell time for the next month.
Insight 5 merges all our data sets and uses k-means to cluster countries by shipping intensity. We filter the seaborne trade data to 2015 to 2023, remove region labels, average each country's trade, and merge it with the clean TU data after fixing name mismatches. After scaling both features, we use the elbow method to pick k and run k-means. The resulting scatter plot shows which countries function as major global hubs, which fall in the mid-tier, and which operate at smaller scales. After scaling the features and running the k-means, we discovered that five clusters were the best fit. This quickly showed which nations operate as major hubs, which fall in the mid-tier, and which have smaller or more specialized profiles.
Putting all our insights together, we found 5 major takeaways. First, global shipping is extremely concentrated among a small group of countries. Second, trade stability varies a lot, with Singapore being the most consistent and China the most volatile. Third, post-COVID recovery was highly uneven, and some countries surged, others lagged behind. Fourth, U.S. ports are improving but still haven't returned to pre-pandemic efficiency. And finally, clustering showed a clear structural groupings in global trade, which help explain international dependencies.
This project pushed us well beyond the standard class material. We learned how to pull data from APIs, how to scrape and parse HTML tables with beautiful soup, and how to clean multi-year international datasets that all had different formats. We also learned machine learning tools like standard scalar, linear regression, and k-means for clustering. Our biggest challenge was cleaning inconsistent data across multiple sources. Each dataset labeled countries differently, used different time ranges, and had messy or missing values, so we had to standardize and merge everything carefully. But more importantly, we learned how to interpret real-world data, not just numbers, but what those numbers say about global markets, port efficiency, supply chain behavior, and economic resilience. Thank you for listening. We really enjoyed working on this project. Have a nice day.